Okay. Hello. I think we should get started. It's already 8:37. Hello. We should get started. Can people in the back hear me? Okay, great. So, well, let's just continue with what we have left in our last lecture. So in our last lecture, we basically, integrate the mole flux, total mole flux equation into, as well as the Fick's law into the mole balance equation, right? That gave us a new set of equations we can really use to solve some kind of mass transfer problems. And we discussed one problem which is a kind of simple problem where we have two bulbs with inside is a binary mixture, and in the two bulbs we have different concentration of component A. Then these two bulbs are connected by a tube, and then we try to solve the molar fraction of A throughout the tube at steady state, and then based on that we can compute the flux, right? So it seems like some students are kind of confused about the whole process. So I figure it might be necessary for me to go over the basic procedures, right? Whenever you are given a problem like this, how do you solve this problem step by step? What are the kind of the logical ways you should definitely take, right? The first step is kind of understand the type of problem and identify the governing equations to be used, right? So when you are like given a problem, first ask yourself, what does this type of problem fit in? Well, in our class, because we have mass transfer and separation, so most examples we're gonna deal with is gonna be about mass balance and mass transfer, right? That's obvious. But take a step back for the whole chemical engineering curriculum, right? You will encounter different types of problems, not only mass transfer and balance. There also could be heat transfer and energy conservation and fluid dynamics, right? That's the step number one. You need to just get a sense about, well, what this problem is asking us to do, right? In our particular problem, we are given two bulbs with known concentration of species A, and they are connected by a tube, right? And the concentration in bulb, left bulb and right bulb are not necessarily the same, which means there's going to be a concentration difference, and we know that that's going to cause mass transfer. As a result, so we have sorry. So here in this bulb we have the concentration of A to be XA0, and on this that we're gonna have, right? And when there's a wall at the very beginning, there's a wall separating the two bulbs here, right? And we know before we remove this wall, we know the concentration in the bulb on the left and right, as well as in the tube in the left segment and in the right segment. But the moment we remove this wall, then there will be mass transfer happening, and the concentration, the molar fraction of A, right? It's gonna dependent on the location, right? Z, right? And Z is changed from 0 to L, right? So then it's also gonna dependent on time, right? Because it's gonna take some time for the whole system to reach steady state, right? We call this period before we reach steady state as a transient stage, right? In this transient stage, the mole fraction of A will not only depend on the location, but also depend on the time. Okay. And then kind of the whole problem becomes if we were to find the flux of A through the tube, actually, if we can find mole fraction of A throughout the tube, then we can compute more the flux of A based on more Fick's law, right? So now the problem just simplifies to a problem in which we need to solve mole fraction of A throughout the tube, right? Now, with that, bearing that in mind, we know the equation we can go to is the mole balance equation, because that tells us in a control volume that tells us how to model the kind of like a mole fraction change or mole balance in a control volume, and tell us kind of the accumulation of a species A is going to be equal to the summation of convective flux plus diffusive flux plus reaction. Right now we have identified this equation, but obviously, this equation is designed to be, universal. Right? It should be applied. Should be able to be applied to any problem, which in another way means it's kind of like complex, right? And then we should, simplify the equation based on the kind of the specifics of our problems. So in this case, we kind of need to examine all the assumptions and see if we can simplify this equation to a form that's easy enough for us to drill down. Then that's when we look at the assumptions. Then temperature, pressure are constant. That means there's no pressure gradient and there's no driving force to flow, which means there's no bulk flow. And that just helps us to eliminate this term. That no reaction, that helps us eliminate this term, right? So bulbs are well mixed. This just means that in this left bulb and the right bulb, the concentration is uniform. There's no concentration gradient, so we don't have to worry about that. 1D domain just means that at some point we can just simplify this equation into its 1D form, right? Because these equations are supposed to be applied to a three-dimensional case, but we'll get to that later. Compositions are known at domain boundary z equals 0 and z equals L. That's just kind of the boundary condition for this problem, right? So now we have been able to eliminate these two terms that left us to this, left term is accumulation, the right term is the diffusive flux. This leaves us kind of a transient problems. We have the dc dt on the left. So if we have that term in our equation, that means C is still going to be dependent on time, which means it's a transient problem. But for simplicity, in today's lecture, we make the pseudo steady state assumption, right? That help us to eliminate this term as well. Right? Pseudo steady state means at some point, our system has reached a pseudo steady state, and the concentration does not change with time. That means we can just eliminate this term, right? Obviously, the system will not go to the steady state right away. The transient period is always going to be there, but that's not something we're going to solve today. That will be something we will worry about later, right? So with this equation, well, not yet. So that has only this term. Now we can further kind of like simplify this equation now. In order to do that, we have to define the control volume, right? Because once we define the control volume, we know the kind of the surface we can integral the diffusive flux with. And based on the nature of this problem, we pick just the tube itself as a control volume. So in this case, this control volume will only have kind of three surfaces, right? Two ends and the wall. And we know the wall is impenetrable to the flux. So that allows us to further simplify, the equation. We can further simplify this term to be, J So we're worried about JA. So minus JA L equals 0, right? So this is from, Monday's lecture. No, so I'm just going to write on the conclusion here. Further, that just give us J. Right. That tell us basically at a steady state, at a pseudo steady state, the flux throughout the tube is going to be a constant, right? So with that, we still need to find a way, right, to link the diffusive flux with the mole fraction, because that's something we want to solve, right? We need to know the mole fraction of A throughout the tube. And then this is when you can apply Fick's law. So we know Fick's law basically relates the diffusive flux with a mole fraction of a species, or more specifically relates the diffusive flux of species A with its gradient of its mole fraction. That's when we can just apply JA equals minus CDAB, because it's 1D problem, so we can just apply derivative. Right, that's kind of like the space. Now this becomes kind of like our Gaussian equation after all this simplification. And now this equation becomes simple enough, right, where we can see we have a derivative here. Now, now that's when we go to step 3. We identify in this equation, we identify which are unknown variables, which are parameters, right? That will help us to better understand, better formulate a strategy to further, solve this equation. When we look at this, we know for sure XA is unknown, right? XA is a mole fraction of A throughout the tube. That's something we need to solve at the very, we know that from the very beginning. Z is just a coordinate, right? And C and DAB. DAB typically we say it's a constant. It's not an unknown. It's usually it's known, and C is a concentration. It's always typically it's known. Then we have J. J here is a constant, but it's an unknown constant, right? But it's an unknown constant. We can still treat it as a parameter that we know. Then we will worry about it later, right? So now we have the variable we need to solve is XA, and XA in this case is going to be a function of Z, right? Because of the pseudo steady state assumption, XA is not dependent on T. So it's only dependent on Z, which is a kind of location. Now, the whole problem, the whole kind of physical problem has been simplified to a mathematical problem, which is to solve this kind of ordinary, this differential equation to get the functional form of XA as a function of Z, right? That's simple enough. Now this is, since after we get to this step, then what is left is only math, right? So mathematically, how do we solve XA as a function of Z? Then that's when we need to examine our math toolbox, right? Typically, there are 2 types of methods. You can solve a differential equation, either analytical or numerical, right? And the condition to solve them is, you can always solve a differential equation with numerical methods, as long as you know the boundary condition or initial condition. In this case, because there's no time involved, so we don't need to know the initial condition. We only need to know the boundary condition, which we know that is here, right? And you can just always solve this. So then another way is to solve it analytically, right? That means we have to derive the unknown variable to be an explicit functional form of space and time, right? For a transient problem, you need to have time, but for a steady state problem, you don't have time, right? So that is to say, we need to find out the functional form of XA Z. It needs to be something, F Z. Okay, so that's how you solve that. For this particular problem, because the 2 variables here are separatable, right? Because you can just move dz over to the left-hand side of this equation, and then this problem becomes integrable, right? Because it's, and we talk about this, how to solve it in our last lecture, so I'm not going to repeat that now. Then we can just go to the conclusion. So what you do here is, just like this, you have this, then you just separate the variable, you integrate the variable on both sides of this equation, then eventually you will be able to derive x, xa, that's kind of an unknown variable, as a function of z, okay? And all the other parameters are known, right? Where you have, the mole fraction of A at the, at the left end of the tube, and you have the mole fraction of A at the right end of this tube. Then you solve it, right? Then we can just make a plot, just to plot the concentration of a mole fraction of XA as a function of the Z. So starting from 0 to, this is Z equals L, okay? This is a mole fraction of A. Now let's assume XA is larger than XAL. So that means at the beginning, we have more A in the left bulb than in the right bulb, right? So then that means this term, right? So I mean, this equation, if we reorganize it, it's XA equals minus XA naught minus XAL divided by L multiplied by Z, right? Plus XA0, right? So I'm rewriting this equation in a way that's kind of like a, so it's very clear it's a linear function, right? So because we want to solve XA as a function of Z. Now this is what we have, right? So this is unknown variable. This is the, the coordinate, and this is the kind of like, from the functional form of this solution, we know it's XA is linearly dependent on Z, right? Then this is going to be the slope of this line, and this is going to be the intercept. So that's how we can draw this. So basically, you have XA 0 here, and you have XAL here. And since it's a line, it's a straight line, we can just draw a line here. Let's see. Okay. Then the slope of this, right? It's a line with negative slope, right? Because we know, XA is larger than XAL. That's kind of our assumption. So XA naught minus XAL is going to be it's going to be positive. So then the slope here, because we have a negative sign here, it's going to be negative, right? That's why it's a line going down, and that's going to be basically consistent with our intuition, where because initially we assume XA is larger than XA0 is larger than XAL. We have higher concentration on the left than on the right. So then the concentration gradient is going to be like slope from left to right. Okay, and the slope here is, XAL divided by. Okay, that's kind of the slope of this line. Okay, and the intercept with the y-axis is XA naught. That's where you get it. Okay. Now we know we get this because we made an assumption about pseudo-steady state, right? Now we can go back to examine if the pseudo-steady state assumption really holds. So in this case, from Fick's law, we know the flux of A is proportional to C dAB grad XA, dXA over dZ, right? So these are constants, right? Concentration and diffusivity are constants. And now in this case, for 1D problem, the derivative of XA over the dz XA over Z is just kind of the slope of this mole fraction profile. Since it's a line, then the slope is a constant, right? This is a constant, right? So we have constant multiplied by constant multiplied by constant. That gives us JA, the mole flux is a constant, right? So, I mean, that just goes back to the starting point, right? Which means, by self-check, our solution is consistent with our starting point, which means at least from this, we don't make a mistake here. Okay. And further, since you have constant flux throughout the tube, then this term, right, just, whenever, no matter what control volume you draw, the influx and, the flux of A going into this control volume and the flux of A leaving this control volume is the same, right? Because JA is constant throughout the tube. That means nothing left. In the control volume, the concentration of A does not go up or does not go down. So it's a constant, right? That is consistent with our pseudo-steady state assumption, right? Okay. So anyway, in summary, my point here is that after you solve a problem, you get a solution. Just think about the physical implication of your solution, right? And ask yourself, does the physical implication, is the physical implication consistent with the assumptions you've made in order to solve this problem, right? If it is, that means you don't make a mistake. If not, then there's a kind of there's a conflict there. Then something must go wrong. Then you have to kind of re-examine the whole process. Okay. Any questions? Now we can go to the second problem, which is evaporation from a beaker. So this problem is also from your textbook, right? So you can just go back to read your textbook to know more about this problem. Okay. So basically the set of this problem is that we have a beaker, okay, which contains liquid benzene, pure liquid benzene. That's kind of species A here. And the liquid level of the liquid benzene is at a distance from the kind of the mouth of the beaker, right? 0.5 centimeter. Now, then above the mouth of your beaker, it's just pure air at 1 atmosphere pressure. That's our species B. Okay. Now, the problem asks us to determine the mole fraction of A in the Z direction, right? Which means ask us to solve if you have a beaker of liquid benzene sitting on the table, how do we know and the mole fraction or the concentration of liquid benzene in kind of like in the beaker from the liquid surface all the way to the mouth of the beaker, right? How do we solve that problem? Superficially, you may say this seems to be a different problem compared to the last one, but in a lot of sense, it's kind of quite similar, right? So it's a binary mixture problem where we have a kind of reservoir here. This is the kind of a liquid benzene here, right? Then we have a reservoir. If we draw a dashed line here, right? So we have a reservoir here where the mole fraction of A is 1. Then we have a reservoir above the mouth of the beaker where the mole fraction of A is 0, right? Assuming, air is well circulated, right? So every liquid benzene kind of like a vapor will be carried away by the kind of circulating air. Okay. Then since if the kind of distance from the liquid surface to the big mouth of the beaker, 0.5 centimeter, is much smaller, right? This is kind of your delta, your L here. This is your L. If let's say the size of the beaker is R, right? If L is much smaller than R, then we can make a fairly reasonable assumption that we can simplify this problem to a 1D diffusion problem, right? We don't have to consider the variation of A, the variation of the mole fraction of A in the in the radial direction of the beaker, right? So that just simplify this problem again to a 1D mass transfer problem. Okay, now we can apply the procedures we just talked about to solve this problem. Step number one, you identify the governing equation, right? Which is again this mole balance equation, and the goal is to solve for XA as a function of Z. Now step two, right? This is step one. Step two, we need to simplify this equation, right? And by examining possible assumptions, right? Obviously, there's no reaction here. And again, we can still assume steady state, right? Because we don't care about, in this case, we don't care about transient state. Assuming that the beaker has been sitting on the table for long enough and it has reached steady state. And again, we can also do the same assumption, right? If there's no pressure gradient, right? Because it's sitting in atmosphere, given sufficient long, the pressure should equilibrium. So should reach equilibrium. So there's no pressure gradient, there's no flow, or at least the flow is kind of like negligible. Then again, give us this, right? And we know we're very familiar about that, right? And for that, we can just do the just similar like what we did in last problem. So then if you do the derivation, you will figure out, sorry, let me put it here, this is assumption. So we will find out, JA, we need to define the coordinate, right? So this is X, okay. So this is Z equals 0, right? This is Z equals L, right? We need to define the coordinate. JA L is gonna be equal to JA 0, right? And the JBL is gonna be equals to JB 0 at a steady state, right? Whatever evaporates from the liquid benzene, the flux will be the same throughout this mouth. Okay. Well, actually, so let's take a step back. Actually, that's probably a very too strong assumption. Let's remove that, right? So here again, maybe let's use this equation instead. So we use this, right? Okay. I mean, we can still do that, but that just reduced the problem to be the same as the previous ones, which is we don't want to repeat the same problem. So I just want to give a different problem. Now let's do this. Let's not assume there's no there's no flow. Then let's just look at this total mole flux. Then again, this term vanishes. Then we look at this total mole flux, right? And and if you expand this, you will get NA L equals NA 0, NB L equals NB, sorry. Yeah, oh, sorry. This is A, right? So A is benzene, B is air, okay? Now, because we know air cannot going to liquid benzene. At a steady state, let's assume liquid benzene already is saturated with air. So it cannot dissolve any more air. Then there's no way, so in this direction, NB, at this point, NB is going to be 0, right? Because liquid benzene cannot take any more air. It's already saturated with air. So the flux of air going to the benzene is going to be 0. Again, we are doing steady state analysis. So this is steady state. For transient state, story will be different. That just says 0, right? But Na cannot be 0, right? Because Na can evaporate, leaving the kind of leaving the liquid, and then further dissipate into the air. Okay, and then total flux N equals Na plus Nb. It's gonna be because Na. Okay. Any questions here so far? No. Now, yeah, basically from mole balance, we know Nb is 0, so the total mole flux of A and B is just equal to the total mole flux of A, right? The next, because it's a constant, right? We can apply similar methodology to relate mole flux with mole fraction, right? By using Fick's law. That way we can relate, so we can relate, well, we start from this total mole flux equals, mole fraction of A multiplied by the total mole flux of A equals the mole fraction of A multiplied by the total mole flux of A plus B, then plus the diffusive flux of A, right? That's kind of the general equation for describing mole flux. Now, because N equals Na, right? Nb is 0, so we can just replace N here with Na, right? Now, we have Na on the left-hand side and right-hand side of the equation. So we kind of write here. So we have Na equals Xa Na plus Ja, right? We don't know about Na, but we know for Ja, we can relate Ja with Xa, right? In order to do that, we need to move this term to the left. So you have Na equals 1 minus X. Na multiplied by 1 minus Xa equals Ja, right? You can rearrange this. You get Na equals Ja divided by 1 minus Xa. Okay. Now you just plug this back here, right? Because we have Na equals this, right? Now we can apply Fick's law. We replace Ja with the definition of Fick's law. Ja is proportional to concentration, diffusivity, and the derivative of Xa over Z. Okay, and Na is as a constant, as we proved here. Now this equation becomes kind of similar to what we deal with in the previous example, where we have a differential equation where Xa is an unknown variable we need to solve as a function of Z. Then if we can separate Xa from Z, then we can solve this differential equation analytically, right? And luckily what we can do here is this equation is still simple enough. So what you can do is that you move dZ and CdAb to the left of the equation, right? That gives you minus Na divided by CdA dZ. Then on the right-hand side, you have dxa divided by 1 minus, xa. Then you can do an integral. You can do an integral from z0 to z, okay? Because these are constants, you can just take them out. You can take them out from the integral, right? Now, what is left is just to solve this integral, right? This will give us a constant, and this give us the log of 1 minus xa, right? So we can just move on, right? So this is kind of our equation from the previous slide. If we solve this integral, it gives us this, right? So one thing we need to be cautious is that when you compute the integral here, you need to make a further modification, which is because this has minus xa here, so you kind of need to let me write it here. You kind of need to write it in this way. Right. Right. So you have to modify this into this form. But by doing so, you introduce a minus sign to xa. That needs to be compensated on the left-hand side of this equation. So that's why you also need to, add a minus sign to the left-hand side. Right? So that gives you a C, D, A, B, right? So it already have a negative sign. If now you give it another negative sign, they just cancel each other. Give you Z. Okay. And this is when we can, solve this integral. We know this is just a C, D, A, B, Z minus Z 0. On the right-hand side, you have a log, right? Then this is going to be log 1 minus xa divided 1 minus xa. Okay. Then if you rearrange this equation, you get this. Okay. So, but anyway, so you can rearrange this equation. You can get the flux equation. You can also get the xa as a function of z. Okay. Now with this equation, the only thing that's unknown is just xa, is na. But this is something you should be able to solve by plugging. Na should be able to be computed by computing the evaporation rate, right? That's something we can do from thermodynamics. Then you get Na, then you will be, and then with this equation we can compute xa as a function of z. Okay. Questions? So this problem is kind of quite similar to the previous problem. Kind of the only difference here, not kind of two difference. One is instead of assuming there's no bulk flow, we don't do that. So we start from Na. We can still prove Na is constant throughout at a steady state throughout, this kind of tube. But now at the end you find out that the fixed equation is somewhat modified by a factor of 1 minus xa, right? Fixed law does not have this term, but now if you consider convective flux, then we can modify the fixed law by this factor, so then the fixed law can include the effect of convective flux. Now, so long as 1 minus xa, 1 minus xa here accounts for the convection, right? And we know that if xa goes to 0, that means if the mixture is dilute enough, when XA goes to 0, then 1 minus XA goes to 1. 1 minus XA goes to 1. Then this equation just reduced back to Fick's law, right? And the physical meaning of this is that here in this control volume, we have a mixture of benzene vapor with air, right? This is a binary mixture, right? If the mole fraction of benzene, right, which is species A here, is very small, then its convection is just negligible. So we can just use the Fick's law to describe its total mole flux, right? And mathematically, it is manifested in this kind of like a term, right? If it's very dilute, XA goes to 0, then 1 minus XA just approximates 1. Yes?
How are we able to know that there's no air in them? Was an assumption made within the problem statement? There should be some air.
Yes.
Small amount, right?
So there will be air dissolved in liquid benzene if we start to solve this problem by assuming the system has already reached steady state, right? Because steady state means you put that beaker of liquid benzene on the table for, as long as, for so long, if air wants to dissolve into liquid benzene, it already does so. And it's already saturated with air, which means there's no more air can be dissolved into the liquid benzene. Okay.
So are we assuming this is already at steady state or not?
Yes, we assume it's at a steady state. That will greatly simplify our problem. Okay. And so far we haven't dealt with transient problem yet. But I just want to give you a flavor, right? So a lot of times steady state assumption can be powerful, and it's a valid point, right? Like I said, if given enough time, every system will reach either steady state or equilibrium, right? We just don't, and that will just save us a whole lot of brain cells to solve the problem. So just give it some time, then we will save time. Okay, good.
Yeah, actually, another question.
Yes.
Sorry. So why do we know that NB is 0 at L and at 0? Because shouldn't there be moles of air in the system in the state?
Yes. So let's come back to this point, right? So let's see what could happen, right? So there's air here and there's liquid benzene here, right? So then we have in this control volume, we know that there's going to be a mole flux of B going downward, right? Because there's more air in the top than in the bottom. And then at the bottom surface of this control volume, there's also going to be NB, right? So this is NB0 and this is NBL. In transient period, right? That's before we reach steady state. NBL is not 0 because we know given time, air is being dissolved into liquid benzene. Even though it's slow, it happens. But at steady state, right? Because we know we made the steady state assumption, liquid benzene is already saturated with air. There's no way air can go into liquid benzene, right? Just like, and before the classroom is kind of like empty. There are plenty of seats available for students to come in and take. But now, let's assume this is a very popular class. And even before the class, all the seats are taken. There are no more seats. And now, Nathan, you're late, right? You open the door, you want to get in, but there's no seat. Sorry, you cannot get in. There's no flux of Nathan getting into this classroom. Does that make sense? Okay. Good. So we want to add some comments on Fick's law so you understand, the physical meaning here. In this class, we typically assume the total mole concentration is constant, right? If there's no reaction, this is really kind of typically valid, right? Because there's no reaction, there's no creation of species. But that does not mean C is constant, right? Because C is C multiplied by mole fraction of A, and mole fraction of A can still be a variable throughout the volume the control volume we are studying. But with C to be a constant, it does not depend on space. That allow us to just plug C into the gradient operator that can just convert this equation to that, right? So this is another common form of Fick's law, right? This is kind of the very beginning. This is the very beginning. I said the diffusion, the driving force of diffusion is the concentration gradient. Okay, and this is reasonable for isothermal, isobar system, or liquid system. And so far, we have only considered binary system, right? And because it's kind of simplest case we can deal with. If you go to multi-component systems, things become quite complex. And there could be other driving force for the mass transfer, in addition to concentration gradient or mole fraction gradient, right? For example, pressure gradient, right? That's in the centrifuge, you're creating a pressure gradient that will cause some mass transfer. There could be thermal gradient, right? And this happens, I mean, if you look at, let's say, I mean, if you make a cup of tea, and if you add some hot water into the tea, you put this glass of water under light. And if you have a very, very good vision, you will probably see, the mixing happening. And part of that is due to the temperature difference. So in general, chemical potential is the driving force for diffusion. So I think you guys will deal with chemical potential in your thermal class. But in review, chemical potential, by definition, is the kind of summation of a reference state plus RT log A is the activity, which can be further breakdown to be, to be the activity coefficient plus concentration, right? Now, from this equation, you can see temperature plays a role here, concentration plays a role here, and the non-ideality of your solution plays a role here by the factor of the activity coefficient. Right? So that's something you will deal with in your thermal class, which I'm not gonna spend, dive into. Okay. Great. I guess time is up. We can stop here and we'll continue on Friday.